Somewhere out in the universe, gravity can freeze a person in time, fall toward a black hole, and to everyone watching from a safe distance, you never actually fall in. You slow, you redden, you stretch, and then you hang at the very edge, glowing, fading for the rest of time. But from where you're falling, none of that happens. You drop straight through, wide awake in seconds. Same fall, two endings, both of them completely real. This isn't science fiction, and it isn't a trick of the story. It's just where the laws of physics begin to bend. And tonight, we are going to follow them all the way down to the one place where those laws stop working entirely. So what is a black hole really? Forget the word hole. It isn't an opening. It isn't a cosmic vacuum cleaner. It's an object, a mountain of matter crushed into so small a space that gravity around it becomes almost unimaginably strong. Strong enough that, past a certain line, escaping would mean outrunning light itself. And nothing outruns light, not a rocket, not a radio signal, not even a scream. That line has a name, the event horizon. It isn't a wall. It isn't made of anything at all. It's simply the boundary where out stops being a direction you can choose. Now, what actually happens to your body? That depends entirely on which black hole you fall into. And the answer is the opposite of what you'd guess. Take a small one, 10 times the mass of our sun, squeezed into a ball the size of a city. That's the killer. Its gravity changes so sharply over just a few feet that your toes are pulled far harder than your head. That difference stretches you, thins you, draws you out into a long human thread. Scientists really do have a word for this, spaghettification. And near a small black hole, it tears you apart long before you ever reach the edge. A supermassive black hole flips the whole story. These are the giants that sit at the hearts of galaxies, millions, even billions of times the mass of the sun. Ours is called Sagittarius A star, and it weighs about 4 million suns. That's a single dark object as heavy as 4 million stars hiding at the center of the Milky Way. You'd expect something that enormous to be far more violent. It's the reverse. The bigger the black hole, the more gently its gravity changes across your body at the horizon. So here, you could cross the point of no return completely intact. No stretching, no pain, nothing at all. And that is exactly the problem. You might sail past the edge of forever without feeling a single thing. Because the event horizon gives you no warning. There's no barrier, no flash, no line painted across space. One moment you're outside where escape is still possible. The next, you're inside where it never will be again. And there's no way to feel the exact instant it happened. And here's the part that breaks people's intuition. Once you're past the horizon, the center of the black hole is no longer a place ahead of you that you could steer around. It becomes a moment in your future as unavoidable as tomorrow. Fire your rockets in any direction you like. Every path you can still take now leads to the same place, inward. And as you fall, time itself splits into two stories. To that distant observer, your clock runs slower and slower as you near the horizon. Your light takes longer and longer to climb back out to them, stretching from red to deep red to nothing. From the outside, you never quite cross. You freeze at the edge and fade. But from your own seat, none of that is happening. Your clock ticks along normally. You cross the horizon in a matter of seconds, alive. Watching the universe behind you, two observers, one fall, two endings that flatly contradict each other, and both are true. Neither one is an illusion. That's simply how gravity bends time. So what does the universe actually look like from inside the fall? As you drop, the sky ahead of you begins to crowd together. Our best calculations suggest that all the light of the outside universe, every star, every galaxy bends and gathers into a shrinking, brightening circle above you. Everywhere else, darkness. You would be watching the entire visible cosmos funnel into a single porthole of light, growing smaller as you fall away from it. The entire sky, gathered into a bright coin you could cover with your thumb. It may be the most beautiful and most terrifying view that nature can offer. And it does not last long. Ahead waits the thing every path leads to. We call it the singularity. In the mathematics of general relativity, Einstein's theory of gravity, and the finest one we have, it's a single point. A point where all that mass has collapsed as far as collapse can possibly go. The density climbs toward infinity. Space and time curve infinitely tight. For a supermassive black hole, you'd reach it just seconds to minutes after crossing the horizon. And this is where the honest part of the story begins. Because when a physicist's equations start printing the word infinity, it almost always means one thing. The theory has hit a wall. General relativity is one of the most successful ideas in all of science. It predicts the orbits of planets, the bending of starlight, the ticking of clocks, down to astonishing precision. But at the singularity, it hands us infinities that cannot be real, and then it goes silent. To know what truly happens in that final instant, we'd need a theory that fuses gravity with quantum mechanics, a theory of quantum gravity. And after a century of our very best minds reaching for it, we still do not have one. So the honest answer to what is at the center of a black hole is not a dramatic reveal. It's 3 quiet words: we don't know, and that isn't a failure. It might be the most thrilling sentence in all of physics. Yet this part is crucial. None of this is a fairy tale. Black holes are as real as the moon. We have watched stars whip around an invisible object 4 million times the mass of the sun at the center of our galaxy, work that earned a Nobel Prize. In 2015, we felt the ripples in spacetime as 2 black holes slammed together a billion light-years away. And in 2019, humanity did something once thought impossible. We took a picture of one. A dark silhouette, ringed in fire, sitting exactly where the theory said it would be. There's one last twist, and it may be the strangest of all. Stephen Hawking argued that black holes might not be eternal after all. Thanks to the strange rules of quantum mechanics, they should leak the faintest trickle of energy, a whisper of light we now call Hawking radiation. And over spans of time so vast they make the current age of the universe look like nothing, a black hole should slowly shrink and finally blink out, if that's right. A black hole isn't a final resting place. It's just the slowest death in the cosmos. And whether anything that fell in ever comes back out, physicists are still arguing about that today. So here is where the fall really leaves you. Cross the horizon of a giant black hole, and for a few strange, silent seconds, you would drift in peace. Behind you, the entire universe would shrink to a single point of light. And ahead of you waits a center that our deepest theory can describe right up to the final instant, and then cannot describe at all. Not because we aren't clever enough yet. Maybe because a black hole is the one place in nature built to keep its own secret. So I'll hand it to you. If the laws of physics themselves come apart in there, what do you think is really waiting at the center? Tell me below, and I'll see you in the next one.